Ooh, okay. Field lesson number 4. Great. Magnetic fields.
Sorry, tomorrow, yesterday we did 2 lessons. First is electrical formula.
A tutorial and a lecture then, yeah.
Tutorial and then
Yeah. Okay, here we go. Magnetic field. Goodness. Okay. You got that? Magnetic field. Okay. So, there's a good bit to do, unfortunately. Right, so you know what a magnet is, don't you? Here's a picture in case you forgot. So a magnetic field is the area around the magnet in which there's a magnetic force. A moving electric charge can make a magnetic field. So we'll do this bit by bit. So first, just get this bit. Magnetic field is the area around the magnet, firstly. You got that? Yep. Now, I know this is a magnet, but how can you make a magnetic field? In fact, one way to make a magnetic field is if you have a moving electric charge. So when you have a charge that moves, you can make a magnetic field, which is something we'll look at more later. Magnetic field can usually be seen by magnetic flux line. So there's a lot for this definition. I know there's a lot. The next part is something called flux lines, which are the name of the lines that come out of the magnet, which I'll show you in a picture in a moment. Or maybe I'll just quickly show you here. But I'm sure you've seen this in middle school, maybe. You have your magnet north, south, and you imagine you have these lines that come around it. You remember this from middle school, don't you? Yeah, these are called the flux lines. We'll talk more about that later, but that's what I mean here, that magnetic fields can be seen by the flux lines. Okay, so if we can write the rest of this definition down. I know it's a long definition. cut this?
Mm,
Get too cold?
I know, I can see.
Ah, yeah, no. Yeah, you can move, you can move. I should fix this also.
Oh. So bad.
I don't know, is that any better? Not really, is it? Yeah, I guess it's a bit better. Okay, continue. Yeah. Right. Next. So there's a beautiful picture of the flux lines. So first notice that it goes from north to south, and you have these loops here around there. You've seen this in a picture in middle school of this, haven't you? Yeah. But maybe what you haven't seen is the direction. So please, when you draw this, make sure you have the arrows to show the direction. So it's from north to south. These are the flux lines. And sometimes they ask you to draw things like this in the exam. So can you draw a beautiful picture, please? Did you draw? Yeah? Yeah? Okay. Next. So, I'm sure know this again from middle school, but you know that it's like there's a magnet inside the earth. But what you need to be careful about is it's not maybe the way you think it is. So for example, what's the one up the top called? Is it north or south? Yeah, but it's not actually. Which I know seems odd, but let me show you. So here's Earth. Come on. There we go. Right, so here's the magnet inside. There's like a magnet in here. And it actually is like south on the top and north on the bottom, because if you have your little compass, the north is on the top and the south is on the bottom, because remember, the opposites attract. So if you want the north to point up, it must mean there's a south on the top. So I know we call it north, but it's actually south of the magnet. Yeah. There we go. So you can try and draw this. Don't worry. Well, it doesn't have to be as nice as that. You know, what I want to see is just, you know, something like this, and then you can put the lines in, going around like that. You know what I mean? Make it a little nicer, maybe. My ugly picture? Okay.
Can you go back to another picture?
The pretty picture, yes. I want a simple picture. Oh yeah, it's from the bottom all the way to the top, yeah. Is that what you mean? Yeah.
Operative like S for the typical Morse mark.
I know, it doesn't make sense. Okay, continue? No. I'm not drawing. Show me what you're drawing. You're drawing it too nice, I think.
It's drawing nicer.
Ah, no, too nice, too nice. Let me see, Andy. Yeah, this is what I want. Sonny, let's see. Yeah, this is what I want, Shireen. I'm continuing. Yes, continuing. Okay. So if you remember, I said in the definition that when you have a charge that moves, you have a magnetic field as well. So what I mean is, if you have a positive charge and it's moving, it will make a magnetic field as well as it moves. And you can see that in this picture. So here there's no current. Nothing happens. They all point to the north. But then, when I turn the current on, you can see all the compasses, they move. So what's happening here is there's a magnetic field that's being made, and it goes around in a circle around the current. So as this is moving, it's making a magnetic field around it as it moves. It's making a field around it.
So it's the right-hand grip rule.
This is it, yeah. So I don't know, do I say that in the next slide, or do I have to tell you here? Oh, no, I have to tell you. So you can use something called the right-hand rule. Your thumb is the direction of the current. So in this case, the current is going up. So your hand here shows you the direction of the magnetic field. So here you can see that if the current is going up, the magnetic field is going around like this with your fingers. This is called Fleming's right hand rule, the right hand grip rule. Yeah, so if the current is going down, it's going around the other way. Yeah? Okay, next. Can you draw that roughly? Yeah, this one here, remember the direction goes around this way if the current's going up. Yeah, continue. Okay. Now, there is another way to make a magnetic field. Let me show you. So one other way you can make a magnetic field is you use something called a solenoid. So you know, because there's a current, there'll be a magnetic field around the current, yes? If you make a loop like this, what you can do, actually the picture's a little bit small. Let me just put the arrows going the other way so it matches up with my picture. So it goes up, yeah, so it'll be going around like this. But when it gets here, the loops, it causes the magnetic field to loop in total like this. In other words, you can see it better in my picture. When you have a loop like this, it's like you have a north-south magnet like this. It's like you have the same thing as this. So when you are able to do this, like for example here with the wire, if you can loop the wire around like that, then you get a magnetic field here, just like a north-south magnet. Okay. So you can see it's actually very easy to make a magnet with a current. I'd like you to try and draw this picture. So this is called a solenoid. There it is there. And a solenoid is the same, it makes the same magnetic field as a bar magnet.
Do you have to put something inside the thing?
You know, I used to think so too, but you don't have to. But usually people put some soft iron core. But it turns out technically you don't have to. Yeah? Can I continue? Did you draw that? Yeah? Okay. So I just want to clear up two things. The last picture, okay. So I did that already. Yeah, no, I told you this already. This is called the right-hand rule. So I told you this already. And a solenoid is what you drew for me. Did you write down its name, the solenoid? A solenoid is a coil wound into a tightly packed helix. If you want to write that down, you can. Helix is the name of the shape. That's a helix. Yeah? Continue? Okay, so that's a solenoid. Right, so far we haven't said anything about the units, you've noticed. I've just drew pictures and talked about fields. We haven't said anything about the units, so we need to talk about the units. So how do we measure a magnetic field? So we use something called magnetic flux. And the magnetic flux over a piece of space is the number of magnetic field lines through that area. And the SI unit is the Weber. So I'll just draw that, just so you're clear. So for example, here's north, here's south. And here's the area. So here we say there are two Webers. There's two magnetic field lines here going through this area. So on this there are two Webers. Okay, this is called magnetic flux. It's just the number of lines. So 2 Webers. And in fact, although I won't show you why, but in fact the Weber is also the same as the volt second, but that's not something that we'll have to do. So magnetic flux over a particular area is the number of magnetic field lines through that area, and the SI unit is called the Weber, WB.
Is that the symbol for magnetic?
Yeah, it is, yeah.
How does it look like a rocket?
It looks like a what?
It looks like a demon symbol.
No, I don't think so. Got it?
So,
Yeah? Okay. So Heath and Andy. Ready? Yeah? Okay. Magnetic flux density at a particular point in a magnetic field is the amount of flux per unit area perpendicular to the field. The unit is the Tesla, which is just 1 Weber per meter squared. So as a formula, it's flux divided by area. So it's nearly the same. So for example, here you have the magnetic flux is 2 Webers. And if you knew the area here, let me call the area A, then we say the magnetic flux density is 2 divided by A. So I don't know, let's say the A is, 2 meters squared. Then in this example it'd be 1, and the unit we call is Tesla. But Tesla is just Webers per meter squared. So I mean, it's nothing major. This is why we call it a density, because it's divided by an area.
Did Tesla make that related?
Yes, Tesla is a person, yeah. You know Tesla, don't you? Yeah. So this formula is useful. The magnetic flux density is the magnetic flux divided by the area. Yeah? Got it? Great. Great. Okay. So you don't have to write it down, but just so you know, the B is the nearest thing we have, which is like an E for an electric field. So a B for a magnetic field is a little like the E for the electric field, okay? Although the units are not quite the same, similar. So a moving charge, who are you talking to? You sure? Yeah, okay. So a moving charge will produce a magnetic field. And by using the right-hand rule, we can know what the field looks like. If the moving charge in a magnetic field, then it'll feel a force. You know this from life. If you have 2 magnets and they push against each other, you can feel it. North will repel north, and S will repel S, but N and S will attract. So if you think about it like this, if you have a north and an S, they'll be attracted to each other, right? And if you have a north and a north, they'll be repelled. So if you have a magnetic field, north-south, and here is an electron, and the electron is moving along, because the electron has a charge, it will produce a magnetic field around itself as it moves. So what happens when you have two magnets together? You get a force. The force can pull them together, or the force can push them away, but you still get a force. So the question is, how big will this force be? So for example, with an electric field, you know that F equals QE. What is it for a magnetic field? So it will depend on the B, it will depend on the Q, and it also will depend on how fast the charge is moving, the V. So the formula will be QVB, and this is a special multiplication which I'll talk about in a moment. This cross is a special type of multiplication known as a cross product. So it's the formula QVB which I care about right this moment. So can you write this down? This is a bit like QE. It's the same idea. So I just need the formula. You can write this down as well. Force F on a charge Q in a field of flux density B while moving at velocity V is. You got this formula? Yeah? Continue? Yeah? Okay. So let me explain a little bit more about the special multiplication here. So let's keep it simple. Let's say there's a north here and a south here, so the field is going down like this. And there's a positive charge here, so the current is going to the right here. This is I. So the question is, which way will the force act? So will it move up? Will it move down? Will it move right? Will it move left? That's what the cross here is for. This tells us that the special multiplication, that the answer is QVB, and the direction is using the left-hand rule. Left-hand rule. Now let me show you with my left hand. This finger is the force. This finger is the magnetic flux density. And these fingers here, these are the eyes. So if I take my hand, this is the force, this is the magnetic field, and this is the current, I. So you try and match it up with the picture here. The current is going to the right, the magnetic field is going down, so then the force is going in. So what will happen is, this will come along and get pushed into the page. So it turns left Can you see that? No. This one here is the magnetic field, so that's going down. This one here is the current, that's going right. Yeah, so then the force is going into the page. So the force is that way, straight.
Wait, this is the force.
Yeah.
This is the magnetic.
Yes. Makes sense or not? It does. Yeah. Continue. So this is called Fleming's left-hand rule. So if you want to try and draw this hand, please do.
Can you write down the force?
Yeah, just force, yeah. Let's see your hand. That's funny. Not bad. Let's see your hand. Not bad. Interesting. Kind of looks like a dog. Alright. Continue? Yeah. Right, so after all of this, we can now have a look at our first type of question. Okay. Can you write this one down? A ferromagnet has flux of 2 Webers, and the region is a circle. Okay, so write this one down. So, in fact, you only have 2 formulas for today. You need the first one for this one.
So now you take 1 final step and you take 2 final steps together, it's simple.
The level is similar, but the questions will be different. The person who writes the physics exam, he keeps the questions different between the different versions for intake 1 and intake 2. However, the maths person doesn't do this. They're more, the maths exams are more similar in intake 1 and intake 2, whereas the physics exams, the person who writes it makes more effort to make them different. So, yes, the intake 1 maths exam will be useful to you. The intake 1 physics exam is not really useful. Yeah, just a practice, yeah. Okay, can I do this one? Yeah. So, you have north-south. What was it? 2 Webers, was it? Yeah, 2 Webers. And the region was a circle. So the magnetic flux density is magnetic flux over area, which will be 2 divided by pi r squared, which will be 2 divided by pi. What's the radius? So 1 centimeter?
Yeah.
Yeah? (6.366 Tesla). Easy enough, yeah? Okay, can we go to the next one? Sophie? Yeah? Yeah, okay. A proton moves towards the east in the Earth's magnetic field. What direction is the force due to the field? Okay, so I want you to tell me this one. You have to use your imagination. Okay. Can I try this one? Yeah? Okay. So, here we are, here's Ireland. Oh no. Oh, no. Getting bad. You know what Ireland looks like. There's Ireland. Okay. So, which way is the magnetic field from the Earth? It's going down this way. Yeah? No. It's, north is actually south. South is actually north. It's going up, yeah. And I say the proton moves to the east. So there goes the proton. There goes the magnetic field. So which way would the force be? So let's see, left-hand rule? Up. Yeah, so which way is the force?
Force is this one, right?
Yeah, so describe
Field is up.
which way the proton will move.
Current is here for the force. Wait, what's the current?
Current is to the right.
The total.
The force will come to us. So the proton will move up into the sky.
Wait,
What?
it's going towards that.
B is...
Oh wait, wrong hand.
I'm tired and hungry. Alright. Okay, so the force is towards you, so that means the proton will move up into the sky. Yeah, so the proton moves into the sky. Now, by the way, this is a proton. If I replace this with an electron, and the electron moves to the right, do you remember from electricity that that means the current is actually to the left? So then the electron would move down to the ground, into the page. Okay, continue. Right, so an electron moves in, if I just got, yeah, this is the last example. Can you write this one down? Okay, you got that? You wrote that down? So which formulas do I need here? Yeah, the second one, isn't it? That you have north, you have south, and you have your electron, and it's moving. Anyways, the formula is F equals Q, I've gone back to using small q, Q, V, B, what's the Q? Is it an electron or a proton? I guess it doesn't matter. It's electron. So that's 1.6 times 10 to the minus 19. The V, what's the V? It says, the question says the V is 1/10 the speed of light. Do you see that? So that's 1/10 times 3 times 10 to the 8. And what's the B, the magnetic flux density?
250 millimeters.
So 0.250 Tesla, yeah? So here I get a small force of 1.2 times 10 to the minus 12 newtons. But I don't want the F, I want the A. So I have MA equals 1.2 times 10 to the minus 12 newtons. So the A, I just need to divide by, sorry, did you say it was an electron?
Yes.
Okay. That's an 18. Let me clean that up for you. That's an 18. Can't see my... I don't ask you where it's moving, I just want to know how much force there is. Okay, you got that one? If it was the way I drew it, if it was the way I drew it, which way would it move?
So,
Which way? No, I think it would move to you.
Okay.
Which way is the current moving? Wait, stop. Yo, stop. Which way is the current moving?
That way.
To the left. FPI. So the current is to the left, and the force is down, the field is down, so the force is to you. So this would move out of the page to you. In fact, this is important. The direction it will go will be around to you like that. Can you see that? This is actually circular motion. It will move in a circle as it moves around to you, at 1/4 circle. So this is why students don't like fields, because it mixes a new topic with mechanics, makes it more difficult. So you won't be surprised if I tell you we'll have to use a circular motion equation. So for example, if I asked you the time, well, you know that the time here, if it moves in a circle, that would be 1/4 the periodic time. And what's the formula for the periodic time for a circle? Do you remember? It's 1/4 2 pi over omega. So that would be pi over 2 omega. Because it only does 1/4 of a circle. It comes along like this and then turns for a quarter. So do we have any way of calculating omega? Do we? Well, you can use this formula, look. F equals m omega squared, or. I have to give you the or, I suppose. Or, wait, no, actually you could use this formula. F equals m v squared over or. Do you know the F? Do you know the F? Yes. Do you know the M? Yes. Do you know the V? Yes. So can you get the or? So let's get the or. Let's do that. So the or is m times v squared divided by the force. And what's the force? 1.2 10 to the power of minus 12. So here you get the or is equal to 6.82 times 10 to the minus 4 meters. You could use this formula for omega. Omega is V over or. Do you know the V? Yes. Do you know the or? Yes. So omega will equal .4 times 10 to the 10 radians a second. So then the time, what do we say? It would be pi over 2 omega
How do you find the omega from the radius?
the velocity divided by the radius, which we just worked out. So the time will be 3.57 times 10 to the minus 11 seconds. So I guess I added in an extra part here, which is to find the time to move around to you. You remember circular motion, of course, I hope, please. Okay, continue. Okay, here you go. You can write those down, or take a picture. Okay, did you get that? So all of those examples are like examples I did. Even the last one where I asked you to calculate the radius. Yeah? Okay. Can I close this? Great.